Hello, calculus students, and welcome to another online lesson regarding probability laws. Today we'll be talking about the various probability laws and how to define them. And our success criteria is that we want to be able to identify the correct probability law needed to solve a variety of probability problems. So it's all about knowing which formula to use when. In terms of notation for today, mutually exclusive events. These are events that cannot happen at the same time. So for example, if I flip a coin, I cannot get both heads and tails at the same time. I cannot be in room 309 and 311 at the same time. One or the other. Both cannot happen at the same time. And those are mutually exclusive events. So we'll see on the next slide that when we have mutually exclusive events, the probability that event A and event B happens at the same time is 0. But I guess I'm getting a little bit ahead of myself, so let's go back to the top of this slide. These are all the probability laws that we have learned so far this semester, or that we will now have introduced. The first one's a new one. This is in your formula packet. It's called combined events. And if you have two events A and B, this equation right here, and again, this is the one that's in the IB formula packet, can be used to find various things. If you know the OR and the probability of two events, you can then find the AND. If you know the AND the two events, you can find the OR. If you know the and the OR and one or the other, you can use algebra to find the missing value. The important thing to notice here is the number of P's that we have. There's one P here, another there, here, and then finally there. The P's stand for probability. Probability is a number between 0 and 1. And so there are 4 numbers that can go into this formula. How many do we need to know in order to use this? We'd obviously need 3, and then the last probability or p-value would be our variable. So in order to use this, you must have 3 numbers, or 3 probabilities, specifically the ones that go in this formula. Other than that, you can use this anytime you want. As long as you have 3 numbers and you know at least 3 of these 4 probabilities, you can use this combined events formula for anything, for independent events, for dependent events, for mutually exclusive events. And again, I've written it here using sort of a straight language, but we're comfortable for the most part using the math speak. That brings us to our second formula, which is what I started talking about here. Also in your formula packet is this formula right here. It's the addition law of probability for mutually exclusive events. And I believe in the formula packet it just says mutually exclusive events. So this says if we know the OR, we can just add together the probability of A and the probability of B. You'll notice that's the same as the beginning of this combined events formula. The probability of A or B equals the probability of A plus the probability of the B. So why do we not have this on our mutually exclusive events? Well, you need to remember that if they're mutually exclusive, A and B cannot happen at the same time. So we already know that this part would become 0, and that leaves the remainder here. Probability of A or B is just the probability of A plus the probability of B. Honestly, they don't even need to give you that formula. As long as you know that the probability of A and B is 0 for mutually exclusive events, then you can just plug that into the combined events formula. But they are very nice, and they gave us that in the formula packet. So once again, the original combined events formula, you could only use when you have at least 3 of those values. For the mutually exclusive, it's self-titled. You must know that they're mutually exclusive. You can't use this unless they are mutually exclusive. And usually they'll tell you that. Or they'll give you enough information that you can figure it out. Conditional probability, we've talked about that. Again, the key word here is usually given or something like that. We only need the formula for tree diagrams and other spots where it's specifically asking us to use the formula. for Venn diagrams and tables, you generally do not need the formula. Finally, we get to independent events. We talked about this formula, I think, on our second lesson, maybe even our first. The idea is that we can multiply together the probabilities of two events, A and B, to find the probability of A and B if they're independent. So what do we need to know in order to use this formula? It must tell us that they are independent. If they're not independent, don't use this formula. If it doesn't say so, don't use this formula. Use one of the others. Again, combined events is the most commonly used one because it always works. We don't need to know if they're independent or not, but we do need, again, at least three numbers. So this is the most important slide from today's lesson. You need to know these formulas, but they're all in your formula packet. The trick is knowing which one to use. Again, combined events must have three of the four probabilities listed. Mutually exclusive, we must know that they're mutually exclusive events. For conditional probability, usually indicated by the word given, mostly used for tree diagrams or when no other information is given to us. And finally, independent events, they need to tell us that they're independent. Oh, so going to our definition of mutually exclusive, I have a simple little example here. If we have 52 cards in a deck, a standard playing card deck, poker deck, a single card is pulled from a standard deck of playing cards. Label the following events as mutually exclusive or non-mutually exclusive. So a king and a heart. Can I pull out a single card that's a king and a hearts? Well, as we know, there's four suits. Each suit has a king. One of the suits is hearts. So yes, there is a king and a heart. That is possible. So that would be not mutually exclusive. If they're mutually exclusive, it couldn't happen at the same time, and this can. So let's look at the next one, a king and an ace. Now every suit has a king, every suit has an ace, and there's four suits in the deck, but there's no single card that is both a king and an ace, so that's not possible. So we would say those are mutually exclusive. A black card and a seven. Well, there's two suits that have black cards, both spades and clubs, and both of those have sevens, so this is definitely possible. So it's not mutually exclusive, meaning it can happen at the same time. And last but not least, a black card and a diamond. Lots of black cards in the deck, half of them in fact. Diamonds would be one of the four suits, but diamonds are red cards, so this cannot happen, and these would be mutually exclusive. All right, now we'll get to actually use some of our laws here. Give myself a little more room. All right, so the probability of event A occurring is 1/2. Probability B occurs is 1/3, and the probability of A or B occurring is lowercase p. Find lowercase b, p, if A and B are mutually exclusive. If A and B are mutually exclusive. So I see the keyword mutually exclusive. So the first thing I'm going to do is write down the mutually exclusive combined events formula. So the probability of A or B is equal to the probability of A plus the probability of B. Now, if this was the normal combined events formula, we'd also subtract the probability of A and B, but we know that if they're mutually exclusive, that is 0. And again, the formula has this, formula packet already has it shortened like this. So that's our mutually exclusive formula. Now let's see, is this going to answer the question? What are we trying to find? It says find P. And what was P equal to? P is equal to the probability of A or B. Oh, that's right here. So that is my lowercase p, which is what I'm trying to find. So this formula should give me my answer. And then the probability of A, which is a number, and that number is 1/2, plus the probability of B, also a number, which is 1/3. So to find these, I am going to add these two together. We need a common denominator when we're adding fractions. And so we can make these both have a denominator of 6, which would be 3/6 and 2/6, which adds to become 5/6. So little p, the probability of A or B, is equal to 5/6 if A and B are mutually exclusive. Now let's take a look at what happens when they're independent. So independent, we should probably use our independent formula. That says the probability of A and B is equal to the probability of A times the probability of B. All right. Well, we're trying to find P. Remember, P is the probability of A or B. This formula does not have A or B anywhere in it, so this will not get me my answer. And yet, I can't use the combined events formula because I only know two numbers at the moment. So if I use the independent formula, I can get a third number, the probability of A and B. So let's start with this formula here. I've got probability of A is 1/2, probability of B is 1/3. So the probability of A and B is equal to 1/2 times 1/3, which is 1/6. Again, that's not what I'm looking for. I'm looking for A or B. But now that I know this, I now have three numbers. If they're independent, probability of A is 1/2, B is 1/3, and the A and B probability is 1/6. So now let's try our combined events formula, which says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Well, A or B is what we're trying to find. That's little p. Probability of A is 1/2, B is 1/3, A and B is 1/6. So if we add these together, we already know that becomes 5/6. 5/6 minus 1/6 gives us 4/6, or 2/3. So little p equals 4/6 or 2/3 if they're independent. One last example. We're just going to do part A here. It says if the probability of Q equals 0.5, the probability of R equals 0.3, probability of Q or R equals 0.75, are Q and R independent? Independent. I see the word independent. So I've got my independent formula, which is the probability of A and B is equal to the probability of A times the probability of B. Well, there's no A's and B's anywhere in this problem, so let's change this to Q and R equals the probability of Q times the probability of R. And now let's find some values. So the probability of Q and R is equal to the probability of Q, which is 0.5, times the probability of R, which is 0.3, and that is equal to 0.15. That's if they're independent. Now, I still haven't answered whether they're independent. I just know that if they're independent, which I don't know, but if they are, this would be the probability of Q and R. So how can we check this? Well, we have other formulas. We have one that is the combined events formula that we can always use. I'm going to cross this out because, again, we're not going to do this one right now. So the probability for combined events is the probability of Q or R is equal to the probability of Q plus the probability of R minus the probability of Q and R. Well, we know Q or R is 0.75. We know that Q is 0.5 and the probability of R is 0.3. And if they're independent, the probability of Q and R is 0.15. Again, this right here, we don't know, but we're assuming it is, and we're going to see if this is a true statement. If this is a true equation, meaning the left side equals the right-hand side, then everything is correct, which means our original formula must have been correct, which means they are independent. If this doesn't work out, then they're not independent. So let's simplify. We have 0.75 still on the right side. I'm sorry, on the left side. If we add together 0.5 and 0.3, we have 0.8 minus the 0.15 that we're not sure about. And when we simplify that, 0.8 minus 0.15 is 0.65. Are these things equal? No, they are not equal. Therefore, are these independent? No. And we have work to prove it. So those are some uses of probability formulas. There are some more examples of this on page 602, numbers 1 through 4, 7, and 8. And again, what we really want to be focusing on is using these formulas, but knowing when to use which formula.